The year was 1982. In a windowless basement laboratory at the University of Maryland, physicist John Wheeler sat hunched over pages of calculations, running his fingers through his thinning white hair. He had just proposed an experiment that would come to be known as the delayed-choice quantum eraser, a variation on Thomas Young's famous double-slit experiment from nearly 2 centuries earlier. Young's original experiment had revealed the wave-particle duality of light, how light could behave as either a wave or a particle depending on how we observe it. Wheeler's new twist would take this concept to a mind-bending extreme by suggesting that our observation now could retroactively determine what happened in the past. The past has no existence except as recorded in the present, Wheeler said to his graduate assistant Thomas Zimmerman, who looked understandably perplexed. By deciding what questions our instruments ask of nature, we create the past. At its core, the delayed-choice quantum eraser experiment would demonstrate something extraordinary, that the very act of measurement not only influences reality but can seemingly alter what has already happened. The implications would shake the foundations of our understanding of reality itself. The quantum eraser experiment, finally performed in full by Marlon Scully, Yoonho Kim, and colleagues in 1999, was not just another quirky quantum phenomenon. It was the culmination of decades of research into quantum mechanics, the branch of physics that describes the behavior of matter and energy at the smallest scales. And what it revealed was profoundly disturbing to our intuitive understanding of how the universe works. To grasp the significance, we need to understand Young's double-slit experiment. When Thomas Young conducted his experiment in 1801, he showed that light passing through 2 parallel slits created an interference pattern on a screen behind alternating bands of light and darkness. This pattern could only be explained if light was behaving as a wave, with the waves from each slit interfering with each other like ripples in a pond. But the plot thickened in the early 20th century when scientists discovered that light also behaves as particles called photons. When individual photons were sent through the double slit, one at a time, they still eventually created an interference pattern as if each photon was interfering with itself. Even more bizarrely, when detectors were placed at the slits to determine which slit each photon passed through, the interference pattern disappeared. The mere act of observation changed the outcome. Wheeler's delayed choice experiment took this weirdness to a new level. What if we delayed the decision to observe which path the photon took until after it had already passed through the slits? Could we retroactively force the photon to behave as either a wave or a particle? It sounds impossible, Thomas said to Wheeler that day in the lab. How can our choice now affect what already happened? That is exactly the point, Wheeler replied. In quantum mechanics, reality is not determined until it is observed. Fast forward to 1999, when researchers at the University of Maryland finally performed a complete version of Wheeler's proposed experiment. They used a device called a parametric downconverter to create pairs of entangled photons. One photon, called the signal photon, was sent toward a double slit. Its entangled partner, called the idler photon, was sent along a different path. Here is where it gets truly mind-bending. By measuring the idler photon in a certain way, the scientists could retroactively determine whether the signal photon went through both slits, like a wave, or just one slit, like a particle, even though the signal photon had already passed through the slits before the measurement of the idler photon was made. The results were clear and consistent with quantum theory. The pattern created by the signal photon depended on how the scientists chose to measure the idler photon, even though this choice was made after the signal photon had already passed through the slits. It was as if the future measurement reached backward in time to influence the past behavior of the signal photon. This is not just counterintuitive, remarked physicist Anton Zeilinger, who conducted similar experiments. It is incompatible with any reasonable definition of reality. The implications extend far beyond the laboratory. If the fundamental particles that make up our world behave this way, what does it mean for reality itself? The delayed choice quantum eraser experiment suggests that reality is not fixed or determined until it is observed, and that the timeline of cause and effect is not as straightforward as we perceive it to be. In 2007, a team led by physicist Alain Aspect took these concepts further. Building on his groundbreaking work testing Bell's inequalities in the 1980s, Aspect demonstrated that entangled particles communicate instantaneously across any distance, violating local realism, the idea that physical properties exist independent of observation and that influences cannot travel faster than light. The world is not how we perceive it, explained theoretical physicist Amanda Sullivan in a 2015 lecture at MIT. What we call reality may be more like a construct, emerging from quantum interactions rather than existing as an objective, independent backdrop. This view is supported by other experiments as well. In 2019, physicists at the Federal University of ABC in Brazil conducted a variation of the quantum eraser experiment using three-slit interference. Their results further confirmed that the classical notion of reality, where objects have definite properties regardless of whether anyone is looking, simply does not hold at the quantum level. Quantum mechanics has been extraordinarily successful as a theory, predicting experimental results with incredible precision. Yet its implications about the nature of reality remain profoundly unsettling. As Richard Feynman famously said, "I think I can safely say that nobody understands quantum mechanics." One of the most influential interpretations of these results is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. It suggests that quantum systems exist in a probabilistic, indeterminate state called a superposition until they are observed, at which point this superposition collapses into a definite state. But other interpretations exist. The many-worlds interpretation, proposed by Hugh Everett III in 1957, suggests that all possible outcomes of quantum measurements occur, but in different, branching universes. In this view, when we make a measurement in the quantum eraser experiment, the universe splits into multiple versions, one for each possible outcome. Then there is the relational quantum mechanics interpretation developed by Carlo Rovelli in the 1990s, which proposes that quantum states are not absolute but exist only in relation to the observer. Different observers may experience different, equally valid realities. These are not just philosophical musings, Thomas reminded his physics students at Stanford in 2022. These interpretations are attempts to make sense of experimental results that defy our intuitive understanding of how the world works. The quantum eraser experiment has profound implications beyond physics. In neuroscience, it raises questions about consciousness and perception. If reality at the quantum level is influenced by observation, what role might consciousness play in the fundamental nature of the universe? We are not passive observers of an external reality, neuroscientist David Eagleman wrote in his 2020 book on perception. Our brains actively construct our experience of the world. Indeed, our brains receive incomplete information from our senses and fill in the gaps, creating a model of reality rather than directly perceiving reality itself. We do not see the world as it is, we see the world as our brains interpret it to be. This is vividly demonstrated by optical illusions, where our visual system imposes patterns and interpretations that do not correspond to physical reality. The famous checkers shadow illusion created by Edward H. Adelson shows two squares that appear to be different shades of gray but are actually identical. Our brain creates this illusion because it attempts to compensate for perceived shadows and lighting conditions. Similarly, the cocktail party effect shows how our attention can filter sensory information, allowing us to focus on a single conversation in a noisy room while filtering out other sounds. Our perception is selective, highlighting certain aspects of reality while ignoring others. Even our experience of time is a construction. Neuroscience experiments have shown that our sense of now is actually a window of about 80 milliseconds that our brain stitches together to create a seemingly continuous experience. Events occurring within this window can be perceived in the wrong order or even simultaneously, regardless of their actual sequence. Time is not what we think it is, explained neuroscientist David Eagleman in a 2015 paper. Our experience of time is actively constructed by our brains. These findings from neuroscience resonate with the implications of the quantum eraser experiment. Reality as we perceive it may be more malleable and observer-dependent than our intuition suggests. But the connections go deeper. In 2022, a team at the University of California, Santa Barbara, led by physicist Matthew Fisher, proposed that quantum effects might play a role in consciousness through quantum processing in neural microtubules. While still highly speculative, this research suggests potential bridges between quantum physics and the mind. If we zoom out even further, to the cosmological scale, similar questions about the nature of reality emerge. The anthropic principle, discussed by physicists Brandon Carter and John Wheeler in the 1970s, notes that the fundamental constants of our universe seem precisely tuned to allow for the existence of life and conscious observers. This observation has led some theorists to propose the participatory anthropic principle, which suggests that observers might be necessary for the universe to exist at all. As Wheeler put it, the universe does not exist out there, independent of all acts of observation. Instead, it is in some strange sense a participatory universe. Modern cosmology presents us with additional puzzles. Dark energy, discovered in 1998 by two independent teams led by Saul Perlmutter and Brian Schmidt, is accelerating the expansion of our universe. Yet we have no idea what dark energy actually is, despite the fact that it makes up roughly 68% of the universe. Similarly, dark matter, which accounts for about 27% of the universe, has never been directly observed, though its gravitational effects on visible matter are well documented. Together, dark energy and dark matter comprise 95% of our universe, meaning that the reality we can directly observe is just a tiny fraction of what exists. We are in the uncomfortable position of knowing that most of the universe is composed of things we cannot see and do not understand, cosmologist Katie Mack wrote in her 2020 book, The End of Everything. This brings us back to the quantum eraser experiment and its implications. If our observations at the quantum level can retroactively determine what happened in the past, if 95% of the universe is invisible to us, and if our brains actively construct our perception of reality rather than passively receiving it, then what is reality? The answer, it seems, is that reality is not what we thought it was. It is not a fixed, objective backdrop against which events unfold. It is dynamic, participatory, and perhaps fundamentally connected to consciousness in ways we are only beginning to understand. In 2015, a team at Griffith University's Centre for Quantum Dynamics in Australia led by Howard Wiseman demonstrated what Einstein famously called spooky action at a distance with unprecedented clarity. They showed that measuring one particle can instantaneously affect another particle, regardless of the distance between them, without any physical connection. These experiments force us to confront the possibility that reality is not locally real, Wiseman explained. That is, particles do not have definite properties prior to measurement, and influences can appear to spread instantaneously. This concept of non-locality challenges our most basic assumptions about the nature of reality. If the universe does not adhere to local realism, then the very fabric of space and time as we understand it may be an emergent property rather than a fundamental one. Some theoretical physicists, including Juan Meldacena at the Institute for Advanced Study, have proposed that spacetime itself might be emergent, arising from quantum entanglement. In this view, the three-dimensional world we experience could be a projection of information stored on a two-dimensional boundary, a concept known as the holographic principle. Space is built from quantum entanglement, explained physicist Mark van Ramsdonk from the University of British Columbia. The way that space is knitted together is through these quantum connections. If space itself emerges from quantum entanglement, and quantum entanglement is affected by observation, then perhaps reality as we know it, including space and time, is indeed constructed rather than objectively existing independent of observation. This brings us full circle to Wheeler's delayed choice quantum eraser experiment. By demonstrating that our measurement choices now can appear to influence what happened in the past, it forces us to reconsider the very nature of time and causality. As physicist Seth Lloyd of MIT put it, the universe is not a machine that grinds along, with time ticking away independently of the events taking place within the universe. Rather, time is defined by the succession of events within the universe. The delayed choice quantum eraser experiment, once forgotten in the shadow of more famous quantum paradoxes, has emerged as one of the most profound experiments in the history of physics. It suggests that reality is not real in the way we intuitively think of it as a fixed, objective existence independent of observation. Instead, reality appears to be participatory, with the observer and the observed forming an inseparable whole. The line between past, present, and future may be more fluid than we imagined. And consciousness itself might play a more fundamental role in the cosmos than we previously thought. These insights do not mean that science has failed or that we should abandon our search for understanding. On the contrary, they represent the triumph of the scientific method, our willingness to follow the evidence wherever it leads, even when it challenges our deepest intuitions about how the world works. As we continue to explore these frontiers, from quantum physics to neuroscience to cosmology, we may need to embrace a more nuanced understanding of reality, one that acknowledges the role of the observer, the limitations of our perception, and the profound interconnectedness of all things. The forgotten experiment that proved reality is not what we thought it was reminds us of a humbling truth, that despite all our scientific progress, the universe remains more mysterious, more complex, and more fascinating than we ever imagined. And perhaps that is the greatest gift of science, not absolute certainty, but an ever-deepening sense of wonder at the extraordinary cosmos we call home.